recording as well. Hello, everyone. Welcome to the recurrent ETDS seminar. So there are many people who are, in the audience who are here for the first time. If you want to be added to the mailing list, please send me or Shilpak an email. We'll be happy to add you. And anyways, so coming to the reason why we are here, it's a great pleasure to have Omri Sarig here for our seminar today, and he'll be telling us about irregularities in the uniform distribution. And over to you, Omri.
Okay, thank you very much, Nishant. You hear me properly? You hear me well?
Yes, perfectly.
Okay. Yes. Perfect. So thank you very much for the invitation to speak at this Zoominar. It's a real pleasure. So the topic I'm going to talk about today is a topic in dynamical systems, but it has a lot of intersections with the other mathematical areas. And what I hope to show to you today is how different mathematical perspectives actually contribute towards the solution. Now, the beginning is at number theory, and it's a very classical part of number theory, which I'm sure all of you are familiar with. It's the uniform distribution of n alpha mod 1. So I remind you the classical theorem of Hermann Weyl, actually, when he was a very young beginning mathematician. And he proved that if alpha is an irrational number, then the frequency of visits of n alpha mod 1, the frequency of visits of n alpha mod 1 to an interval converges to the relative size of the interval. Okay? And this is true for all irrational numbers. Now, what we're going to talk about is a phenomenon called irregularities of uniform distribution. And it is based on the discovery which is the following, that if you look at the error term in Weyl's theorem, then sometimes it has a lot of bias. Okay? It's not evenly distributed or things like this. It sometimes exhibits bias. Now, to study this phenomenon, it is useful to look at the following quantity, dn alpha. So this is the error term in Weyl's equidistribution theorem, but I don't want things to tend to 0, so I multiply it by n so that it doesn't tend to 0. And also, because I want to study the behavior of the number alpha and not the behavior of the interval, I'm going to choose the most symmetric interval possible. Okay? So I'm going to look at the error in Weyl's equidistribution theorem for n alpha mod 1 for the most symmetric of cases, the interval 0, 1/2. So if I take the error term in Weyl's theorem, in this case, and I multiply it by n, then what I get is this expression. Here you have the number of visits of n alpha mod 1 to the interval 0, 1/2 from time 1 to n. Okay, it's the frequency times n, so it's the total number of visits. And here you have n times the limit. Okay? So what you see here, dn alpha, that's the error term in Weyl's equidistribution theorem times n. I'm multiplying by n because I don't want things to tend to 0 so that I can observe the way that they behave. And when people looked at the behavior of this sequence of numbers, they discovered that even for very simple irrational numbers alpha, they can behave in a funny way. Okay? So the most dramatic form of bias was first discovered using soft methods by Yuval Perez and then completely explained by Boschernitzer and Ralston. And they discovered that there are some irrational numbers alphas for which the error term always has the same sign. So it's always either an overestimate or an underestimate. The error doesn't swing around 0, but always has the same sign. So that's a very strong form of bias. A more sophisticated form of bias, more subtle, was discovered by Joseph Beck 15 years ago. And he discovered that for some irrational numbers alpha, you have something called systematic error. So when you talk about error, at least in the physical sciences, it is customary to split the error into a random component and a systematic component, which is like the drift. What exactly this means on the mathematical level in this context, I will explain later. But think about the systematic part of the error, the part of the error that doesn't fluctuate. And Beck discovered that for some irrational numbers alpha, there is a non-zero systematic error that actually tends to infinity. It tends slowly to infinity, but it still tends to infinity. And the final form of bias, which is actually the one I'm going to focus on in today's talk, is something that Dmitry Dolgopyat and I looked at, and that is situations when you look at the sequence of errors, they are not equidistributed in the sense that some possible values of the error appear much more often than other possible values of the error. Okay, again, what this means exactly on the mathematical level, I will explain later. Now, I'd like to emphasize that the irrational numbers for which you get this form of bias are not exotic numbers. Okay, they are not exotic numbers. They are right in front of you. Okay, so this very dramatic form of bias, where the error term always has the same sign, already happens for square root of 2. And the situation when there is a non-trivial systematic part of the error already happens for square root of 5. And the part where some values of the error appear much more frequently than other parts of the other possible values of the error already occurs for square root of 7. If you relook at these choices of numbers, you will see that I skipped square root of 3. And it turns out that square root of 3 does not exhibit any of these forms of bias. Okay, so there is a question here. I think it's an interesting question. What is the reason for the different behaviors of these numbers? Why is square root of 3 much better than square root of 2 or square root of 5? Okay, and this is exactly what I'm going to talk about today. Okay, so let's go a little bit more detail into the different forms of bias. So we already discussed the first one. That's very interesting. That's very easy to understand. There are some irrational numbers for which the error term in Weyl's theorem is always non-negative or always non-positive. Now, what exactly do I mean on a formal level by systematic error? So here is the theorem of Joseph Beck, theorem from 2010. And what he proposed to do was the following thing. He proposed to calculate the first n values of the error term, okay, and then form a histogram. And he proved that for certain alphas, you can fit to this histogram a Gaussian bell-shaped curve. And what he proved was that for certain alphas, for example, square root of 2, this bell-shaped curve is not centered at 0. Okay, it's centered at some other quantity which could tend to infinity like a constant times log n. Okay, so in this scenario, I'm thinking about the mean. I interpret this as the systematic part of the error, and I think about the fluctuations around, which are of the size of the order square root of log n. I'm thinking of this as the random part of the error. But what is interesting is that there is a systematic part of the error that drifts to infinity like a constant times log n. Okay, so now here is the formal statement. So this is Beck's theorem. So suppose alpha is a quadratic irrational. So this means a solution of a quadratic equation, a root of a quadratic polynomial with integer coefficients, for example, square root of 2. And again, I always look at the interval 0, 1/2 because I want to study the angle, not the interval. I want to take the most symmetric possible intervals because I don't want the bias to come from the interval. I want it to come from alpha. Okay, so that's why I look at this interval. And then what Beck showed was that there exist constants, A, that's going to be the systematic component, and sigma squared is positive, A could be 0, it could be non-zero. And then you have a sort of a central limit theorem. So what you do is the following thing. You take the error and you scale it. You subtract a constant and you rescale by square root of log n. So that's a scaling limit. And then you look at how many elements of the sequence of errors are such that this scaled quantity falls inside the given interval. And he proved that you can find A so that there is a limit which is a Gaussian distribution. Okay, so what this is telling you is exactly what I drew before, that if you draw the histogram of the different values of the error terms, then the number of times you fall inside an interval is what the Gaussian distribution predicts. Of course, you need to do some scaling. You need to shift by the systematic component of the error, A times log n, and you need to scale by the width, which goes like square root of log n times a constant. Okay, so this is the formal statement. Now, for us, what is crucial about this theorem is that there are scenarios where A is not 0. okay? And back calculated and showed that if alpha is equal to square root of 2, then indeed A is not equal to 0. And this exactly means that there is a systematic error. He also calculated what happens for square root of 3, and he found that for this number, A is equal to 0, so there is no systematic part of the error. Okay? Any questions about this statement?
So when what you call systematic and non-systematic is about the mean, essentially.
Yes.
Okay.
Exactly. So we are looking about the behavior of a sequence of numbers. They spread around the real line. We do a scaling, and then the histogram converges as an asymptotic shape. And what is interesting is that this asymptotic shape, sometimes it drifts to infinity, in the sense that the center drifts to infinity, sometimes it doesn't. The question whether it drifts to infinity or not is whether this constant A is equal to 0 or not. Okay? This is the A that appears here. Sometimes it is 0, sometimes it is not 0. Okay, so this is Beck's theorem for quadratic irrationals. We now have generalizations of this theorem for other irrational numbers, specifically numbers of bounded type. But we also know that there are no general results like this for a set of even positive Lebesgue measure of alphas. It turns out that for a typical irrational number alpha, when you try to play this game, there will be some sequences where you will see different scaling limits.
I think there's a question in the audience, Omri.
Yes.
Oh, yeah. Can you hear me?
Yes.
Is there a reason why you take the interval to be 0 to half? Like you said, there's some kind of bias from the interval that
this one.
What does that mean? Yeah, the interval. Yeah.
Because I'm interested in the difference between different irrational numbers.
Right.
So I want to study the same interval for all irrationals if I want to compare them. Okay. And the most natural interval to take is the one which has length 1/2, because that's the most symmetric case. You could, and it's interesting to investigate what happens for other intervals. And there are results for other intervals as long as they have rational endpoints.
Right. Okay.
Other questions?
So is there any natural reason why log n factor should appear and not some other function like this?
There is a reason. It will be easier for me to explain the reason later in the talk. Okay, so please remember your question. And if I forget to answer it, then remind me. I'll just say now that it's because there is some renormalization procedure which behaves at an exponential scale, but later you will see exactly what I mean. Other questions? Okay, so we discussed the first form of bias, we discussed Beck's form of bias. But now let's move to what I really would like to talk about, the new part, which is the lack of equidistribution. Okay, so what do I mean by non-equidistribution? So first of all, what do I mean by equidistribution? So I remind you that we are interested in n times the error term in Weyl's equidistribution theorem. So this is given by this formula, the number of visits to the interval 0, 1/2 minus n times the limit, n times 1/2. And if you will look at this expression, you will immediately see that the values are always integers or half integers, because this is always an integer and this is always a half integer. Okay, so all the possible values of the error belong to the group 1/2 z. And now the question is, do some elements of this group appear more often than other elements of this group? Okay, so I will say that the sequence of numbers d and alpha, okay, the error at time n, I will say that this sequence of values is equidistributed in the group of half integers if for any two possible values of the error, so for any two possible half integers, the number of times the error is equal to xc1 divided by the number of times the error is equal to xc2 converges to 1. So this means that xc1 and xc2 appear asymptotically at the same frequency. Now, it's not really a frequency because, as it turns out, each individual value of the error appears with 0 asymptotic frequency. However, if the ratio is equal to 1, then I can still say that they appear roughly the same number of times. You understand what I mean? Okay, so this definition captures a phenomenon, or it describes a situation where all possible values of the error are equally likely. Okay, so this is equidistribution, and we would like to study equidistribution and non-equidistribution. And now let me state the main result, and it's joined with the Dmitry Dolgopyat, so this is Dima. And what this main result is, it's a characterization of the irrationals alpha of bounded type for which Dn alpha is equidistributed. And what you will see once I state this equidistribution result is that it doesn't hold for all alphas. Okay. In fact, for most alphas, it's easier for it not to hold than to hold. You will see exactly what I mean later. Okay, so I need to state the result. I need to remind you some facts on continued fraction expansions. So let's start with just the central notation. So a continued fraction, infinite continued fraction is a limit of nested fractions of this form. And I will denote it in this way. A0 will be the part which is free, which is outside the fraction, and all the other AIs appear inside. Okay. So the regular continued fraction is a continued fraction where the digit at place 0 is an integer and all other digits are natural numbers. Okay, strictly positive integers. And it's a classical fact that every irrational number can be expressed uniquely in this way. We say that the irrational number has a bounded type if the digits are bounded. Okay, say they're all less than 10, something like this. Now, actually, to state my result, I need a different type of continued fraction. I need the even continued fraction expansion. The even continued fraction expansion is a representation of the number as a continued fraction expansion where all digits are even, okay, even integers. Now, of course, because the regular continued fraction is unique, you need to pay somewhere. And the payment is that now they are no longer required to be positive, okay? So the even continued fraction expansion of an irrational number beta is a representation of this number as a continued fraction where the digit at place 0 is an even integer, maybe negative, and the digits at positive places are non-zero even integers, again possibly negative. Okay, and again, it is a fact that every rational number admits a unique expansion of this form. It is also a fact that if the number is of bounded type, that is to say, its regular continued fraction expansion is bounded, then in this case, the even continued fraction expansion is also bounded. It's not an if and only if. There is another property that must hold. Subwords of the form 2 minus 2, 2 minus 2, and so on can only appear with bounded length. Okay, and then it's an if and only if. Okay, so now I'm ready to state the result. So I remind you that Dn alpha is n times the error in Weyl's equidistribution theorem, and that's always a half integer. I'm interested in knowing when is it the case that any two possible values of the error, that is to say any two possible half integers, appear with the same frequency, with the same relative frequency. So this is the case when the number of times the error is equal to C1 divided by the number of times the error is equal to C2 converges to 1. Okay? And now the main result is joined with the Dmitry Dolgopyat. The main result is that alpha, an irrational number alpha of bounded type has an equidistributed sequence of errors if and only if the following holds. So let's take the number 2 alpha minus 1, and let's expand this number into an even continued fraction expansion. Okay, so you can always assume without loss of generality that alpha belongs to 0, 1, and then when you do this beta, we will have an even continued fraction expansion which begins with 0. That's not important. Okay, what is important is that the other digits are all even, maybe negative. Okay, so again, so let's assume that alpha is bounded type, and let's call 2 alpha minus 1 beta and expand it to the even continued fraction expansion. And then the statement is that Dn alpha is equidistributed if and only if the following limit is equal to 0. So what do we have here? K I are the digits, what gives you the digits in the even continued fraction expansion of 2 alpha minus 1. And what we would like is for this average to converge to 0. Now you can immediately see that it's very easy to violate this condition. Okay, you can change the Ki are completely free. You can define irrational numbers in such a way that this limit is not equal to 0 very easily. In fact, it's clear that you can approximate every irrational number by an irrational number which violates this condition. This condition seems to be pretty rare. Okay, what happens for examples? So suppose you look at square root of 3. So you want to see what happens for square root of 3. So you take 2 times square root of 3 minus 1. And believe me that this is the even continued fraction expansion of this number. Okay, it's eventually periodic, and the period is 2, 6, 2, 6, 2, 6. Here there are no sign changes at all, and therefore the limit is 0. In fact, it's identically 0, and therefore you get equidistribution. So square root of 3 behaves very well. On the other hand, if you take square root of 7, you can also do it for square root of 2. If you take square root of 7, then now the even continued fraction expansion does contain a sign change. Okay, the period is 4 minus 2, 4, 10, 4 minus 2, 4, 10, and so on. Okay, now there is a sign change with positive frequency, and as a result, this limit is not 0, and as a result, you do not have equidistribution. Okay, so this is how this theorem works. So again, you will have equidistributed errors in Weyl's equidistribution theorem if and only if the even continued fraction expansion of 2 alpha minus 1 behaves in this way, but this is in fact very easy to violate. Usually it doesn't happen. So usually you do not have equidistribution. Okay, any questions on the statement?
Hi,
So-
sorry.
Go ahead, Nicanor.
Okay, thank you. So previously there was this Beck's central limit theorem and the constant A, which maybe is 0 or maybe it's not. So my question is, the equidistribution of this error term is related to that, or?
Absolutely. Absolutely. So what happens in Beck's equidistribution theorem is it's stated for quadratic irrationals. For quadratic irrationals, it's a theorem that the even continued fraction expansion is eventually periodic. And then, so this limit will exist. It will depend on the period. And if it's not 0, then A will not be 0. A is not equal to this limit, but it's proportional to this limit. Yes. Other questions?
Thank you.
Okay, other questions? Okay, so the rest of the talk is just a sketch of the proof. And as I mentioned at the beginning of the talk, we are going to use several mathematical perspectives to think about this problem. And the first one is going to be ergodic theoretic, specifically infinite ergodic theory. We are going to reduce the problem to a problem in infinite ergodic theory using ideas that in some sense go all the way back to Vich. Okay, we are going to state the problem in terms of something called the cylinder map, or skew product over the irrational rotation. Then we will study this skew product using a beautiful geometric construction due to Pat Hooper, Pascal Aubert, and Barak Weiss. We are going to relate it to the dynamics of something called a linear flow on the infinite translation surface. Then we will use this geometric information to translate the problem to a problem in Markov chains. And now the situation bifurcates, okay? So if you're interested in the case of Beck's theorem, quadratic irrationals, it turns out that the Markov chain that you need to analyze is a homogeneous Markov chain, okay? A Markov chain whose transition probabilities do not change in time, like the one that you think of. And in this case, already 10 years ago, we could do the analysis that is required, and we did it with, in a paper with Avila, again, Dima, and Edward Duryev, and we got the result. If, however, there are only countably many quadratic irrationals, if you want to, so it's interesting to consider other numbers. So if you want to do bounded type, that's already a uncountable collection of angles, which has a full Hausdorff dimension, zero measure, but full Hausdorff dimension. Well, in this case, the Markov chain that you end up with is not homogeneous. Okay, its transition probabilities do change in time. And then we simply did not have the technology required to solve the problem for Markov chains. Specifically, what was missing is something called the local limit theorem. I will tell you later what it is. And then Dima and I worked for something like 10 years just on this problem, okay? And finally, we got it. And once you have this technology, you can use it to solve the problem for inhomogeneous Markov chains. And this is what finishes the proof. Okay, so let's start and discuss this reduction. So we started at number theory, but let me explain to you now how to translate the problem to a problem in ergodic theory. Okay, so here is the translation. So again, we have the error term, but let's make a small modification. Instead of talking about n alpha mod 1, let's talk about x plus n alpha mod. Okay, and now we have the following expression with this x. It's no longer x equals 0, it's an x. And if you look at it, you immediately see that this is a Birkhoff sum. What you have here is a Birkhoff sum for the irrational rotation, okay? So this leads to the following construction, the cylinder map. So you introduce this cocycle. That's the function f of x, the indicator of the half interval minus 1/2. And then you build this skew product. It's a skew product where the fiber is the group of half integers. And as I'm sure many of you know, what's nice about this formula is that when you iterate it, then you get this expression in the second coordinate, okay? This is t of x, this is t squared, and this is tn, okay? You get the error term popping out at the second coordinate, and therefore you can analyze the sequence of errors with x by looking at the behavior of the orbits for the cylinder map. So this is an idea that goes all the way back to Bill Veitch at the end of the 60s. In particular, if I want to study equidistribution of errors, then what is good to do is to take this expression, which appears in the definition of equidistribution, and write it as ratios of Birkhoff sums for the skew product. And you can do it, okay? The number of times the error equals X1 is exactly the Birkhoff sum for the cylinder map for the indicator of the torus times the singleton X1 on the orbit of X0. And the number of times the error is equal to X2 is equal to the ergodic sum, where you sum up the indicator of t times X2, again along the orbit of X0. So now I've taken the quantity in which limit I'm interested, and I translated it into the ratio of Birkhoff sums. And of course, I expect ergodic theory to tell me something about this. Okay, so what does ergodic theory tell me about the ratios of Birkhoff sums? Well, there is the ratio ergodic theorem. The ratio ergodic theorem says the following thing. If you have a t invariant and conservative, so no wandering sets, infinite ergodic measure, okay, and you take two functions in L1 with non-zero integrals, then the ratio of the Birkhoff sums converges to the ratio of the integrals. Okay? Now, in our case, we know that the Haar measure, okay, the product of the Lebesgue measure on the torus and the counting measure on 1/2C, the Haar measure, we know that this measure is ergodic and conservative for the cylinder map. Okay, so there is a long string of results on this. I think the first paper was by Schmidt for square root of 5, and then there were results for quadratic irrationals, and now we know it for all irrational numbers. Okay, so we have ergodicity and we have conservativity, and using these results, this ergodicity and conservativity, we can end the Hopf ratio ergodic theorem. You can get the following consequence that for almost every x, this limit is equal to 1. Okay, so for almost every x, if you look at the behavior of the error terms for, not for n alpha mod 1, but for x plus n alpha mod 1, then you will have equidistribution for almost every x. Okay, so now the question is, okay, can we replace almost every by every? And the answer is no. The answer is no, and it follows very beautifully from results of Hitoshi Nakada, and it works in the following way. There are simply other ergodic invariant measures. Okay? The irrational rotation on the torus is uniquely ergodic, but the skew product is not. The skew product does have other ergodic invariant measures. They were constructed by Hitoshi Nakada. And it so happens that for the other ergodic invariant measures, the limit is not equal to 1. In fact, the typical behavior for the other ergodic invariant measures is that the limit is exponential in the difference of the values. So there is an exponential bias. Okay? By the way, we have a full classification of all ergodic invariant measures. This is in a paper by Aronson Nakada, Rita Solomiak, and me. So we know that these are all the possible typical behaviors, but we also know that there are orbits which are not typical for any measure at all. Okay? So the question, what happens to x equals 0 is a real question. Okay? First of all, it's not clear that x equals 0 is typical for Lebesgue's measure. Maybe it's typical for one of the other measures constructed by Nakada, and maybe it's not generic for any measure. Okay? So in some sense, this is the difficulty. Okay. So to solve this difficulty, it is useful to translate the problem from a problem on skew products to a problem in geometry, specifically the behavior of straight lines on certain translation surfaces. So let me explain this reduction. So it's based on an observation due to Pat Hooper, Pascal Robert, and Barak Weiss, which says that you can realize the cylinder map as a Poincare section for geometric flow. And this flow is the flow in a constant direction on the staircase surface. So what is the staircase surface? So to build a staircase surface, you have to take a rectangle, 2 by 1 rectangle, and you stack it in this form, okay? Infinitely to the up and infinitely down. Okay, then you get this shape. And then you declare that the opposite sides are identified. So this side is identified with this side. And this side is identified with this side. Okay? Similarly, this side is identified with this side, and this side is identified with this side. Do you see my cursor? I forgot to ask.
Yes.
Okay. So now I have an infinite polygon, this staircase, and I define the identification of sides. And I can talk about flowing in a constant direction. So what I do is I take the vector beta 1, where beta is 2 alpha minus 1. Alpha is my angle, and beta is 2 alpha minus 1, the same quantity which appears at the statement of the main result. This gives me a vector. I think of it as a velocity vector. Okay, so it gives me direction and speed. And then what I do is I start at the lower left corner, and I start to move at this constant velocity, okay? Constant speed, constant direction, until I hit one of the sides. When I hit this side, I immediately jump to the one which is identified to it, okay? Then I move again at the same velocity until I hit a side, and then I apply the identification again, and I just continue in this way, okay? So I get a linear flow at constant direction. Now what Pat Hooper, Pascal Huber, and Barak Weiss noticed is that if you take the union of the top sides of the rectangles, you get a Poincare section whose Poincare map is canonically can be canonically identified with the cylinder map. Okay, so where is the cylinder? So you have here, this is like a torus because this point is identified with this point. So this is an interval with 2 identified points. So this is the torus, and the z coordinate is the discrete labels of the rectangles. Okay, so this is where and there is a canonical very simple change of coordinates which transforms this union of red lines to the torus times the group 1 of z, and when you do the change of coordinates, you recognize that the Poincare map gets translated, gets conjugated to the cylinder map. Now, because we are moving at constant velocity, the roof function is constant. Okay, so there is a very simple connection between Birkhoff sums for the Poincare map and Birkhoff integrals for the flow, because the roof function is constant. So it's very easy to pass from one to another, and therefore studying the cylinder map is as difficult or as easy as studying the flow at constant velocity, particular velocity vector on the staircase. Okay? Now the initial condition 0 corresponds to this corner. Okay? The center of the top side of rectangle, let's say, with label 0. Okay, so I have here two slides which explain the conjugacy. I don't have, I think I will skip it because first of all, it's easy, and secondly, I'm running short of time. So just trust me that there is a very, very simple conjugacy which maps a point on the top of a rectangle to a pair in the cylinder space. Okay, let's skip this. So now, once you do this reduction, you get the following consequence. If you look at the error term in Weyl's equidistribution theorem times n, and you count how many times this error term is equal to a particular value, then because of Vich's observation, this is a Birkhoff average for the cylinder map. Because the cylinder map is a Poincare map for the flow at constant velocity on the staircase, this is also the Birkhoff average for the flow. They are the same because the roof function is constant. And now if you think about what's written here, here we are flowing at constant velocity, so the orbit is a line. Therefore, what's really written here is the length, total length of the intersection of the orbit with the rectangle number c. And this is really the length of the intersection of a line and a rectangle on the staircase surface. So we have the following picture, okay? We take the initial condition which corresponds to x0. We flow with the linear flow up to time n, okay? This gives us a straight line which wraps around the staircase surface. And after all these reductions, what we need to calculate is the length of the intersection of the orbit with a particular rectangle. And this is already a geometric quantity. Okay? So after all these reductions, if we want to understand 1 over n times the number of times the error term at Weyl's theorem is equal to a particular value, 1/2 c, this is exactly the same. This can be reduced to the problem of calculating the relative size of the intersection of a line at a fixed direction emanating from the lower left corner on the staircase with a particular rectangle. Which rectangle? If the value we are interested in is 1/2 c, then it will be the rectangle which is x units above the initial condition. Okay, so I have to take a line at a constant direction. I have to wrap it around the staircase surface according to the identifications, and then I have to calculate the length of the relative size of the length of the intersection of this line with a particular rectangle. Which rectangle? If I'm interested at the value 1/2 c, it should be rectangle number c. I'm starting at the top of rectangle number 0. I have to calculate the intersection with rectangle number c. Okay? And that's a geometric problem. Does everybody understand the statement of the geometric problem? Okay, now you can argue, have I really made the problem easier? Because if you think about it, because of the identification on the surface, the structure of the way that this long line wraps around the staircase surface looks very, very complicated. Okay, so it's not completely clear that I've made things simpler, but in fact I have. And the reason is that the staircase surface has many, many symmetries, many geometric symmetries, which are very, very easy to see. These symmetries could, in principle, be translated to symmetries on the number theoretic level, or to symmetries on the level of the torus times the group of integers, but there these symmetries are very difficult to see. On the staircase, they are very easy to see. And we are going to use these symmetries to simplify the problem. So let me explain to you now how. Okay. So first, let me just explain to you what are these symmetries, which are very, very easy to see on the level of the staircase surface, which are present in the number theoretic problem, but are not so easy to see on the number theoretic level. Okay. So here are the symmetries. So imagine that I give you a matrix in SL to Z, which is odd on the diagonal and even off diagonal. Okay. So a matrix of integers, which are odd on the diagonal, even off diagonal, and the determinant is equal to 1. Okay. So it turns out that you can, for each such matrix, you can build a self map of the staircase, which is affine. That is to say, it has a constant, just a second, it has constant derivative. And the derivative matrix is exactly this matrix. It has zero drift. I'm a little bit short of time, so I will skip this. And it commutes with the deck transformation. Deck transformation is the map which climbs the stairs. Okay, so for each matrix like this, I can build a transformation. Now, what I would like to do is I would like to build a transformation that takes my line and contracts it by a lot. Okay, and if I can do this in such a way that the line which I get is so short that it doesn't manage to wrap around the surface even once, then the complicated behavior of wrapping will not occur. Okay. Now, why is it important for me for this map to be affine? Because a map which is affine maps straight lines to straight lines, and it maps the uniform distribution on a straight line, the length to the length. It doesn't preserve lengths, but it preserves relative lengths. Okay, so this symmetry will preserve the geometric feature of measuring lengths along lines, but it may simplify the complications arising due to wrapping around the staircase simply because it shortens lines. Okay, so this is the game we are going to try to play. We are going to try to look for symmetries of the staircase surface, which when you apply to these very, very long lines, shorten them so much that they do not wrap at all, and then they're very easy to analyze. Now, what is so this is what we would like to do. Okay, we would like to take a very, very long line, apply a symmetry, and map it to a short line. Short lines are easy to understand. Okay, there is a complication which is very, very important, which I'm going to mention now, but I'm going to return to later, and that is that these maps may move the starting point of the curve. Okay, they can move it to other rectangles because of certain geometric pathology I don't have time to explain. But just remember this, that these lines may, after I apply the symmetry, they may start at a different rectangle. We'll have to return to this later. Okay, and as I said before, these maps are affine, therefore they preserve the relative lengths along the segment. Okay, so summary up to here, what we could hope for is to find a symmetry of the surface which simplifies the orbit simply by shortening it. Okay, now there is a question, can we actually find such maps? Well, it's not a trivial question because matrices in SL to Z, they like to expand. They don't like to contract. It is true that every hyperbolic matrix has a direction which it contracts, but actually if you're a little bit off from this direction, it may expand. Okay, so it's not trivial to build elements in SL to Z which contract a given direction. The question whether such matrices exist is a question in number theory. And it can be boiled down to the following question. Suppose I give you an irrational number beta. Can you find a matrix in SL to Z which is odd on the diagonal and even off diagonal, which contracts the norm? And the answer is that you can. And here is how you do it. It's a lemma in number theory. You take your irrational number, you expand it to even continued fraction expansion. This is where the even continued fraction expansion appears. And you get this sequence of numbers K0, K1, K2, K3, and so on. Okay. Now you build this sequence of matrices. What you see here are triangular matrices, upper triangular, lower triangular, upper triangular, lower triangular, and so on. It flips. And you build these matrices from the coefficients. It turns out that the product of these matrices will give you a solution. Okay? So, moreover, when you look at how fast vectors are contracted, they are contracted at a logarithmic rate. Now, someone here, was it Kinjal? I don't remember now. Someone asked me about why does log n appear? If you have a quadratic irrational, you can take a periodic, you have an eventually periodic even continued fraction expansion, and then this sequence of matrices is eventually periodic. So you can think about this matrix as the power of the same matrix, and then the rate of contraction is exactly logarithmic. And that's where the logarithm appears. Okay, so summary up to this point. We have reduced the expression n times the error term to a geometric problem of finding the relative size of the intersection of a line with a rectangle. And we are going to try to solve this problem by taking this complicated, very, very long line and applying to it this contracting affine symmetry and shortening it so that there are no more identifications. Now, the green part, the part which we're interested in measuring, the intersection with the rectangle, will be contracted a lot. But what is important is the relative size will not change because it's an affine map. It doesn't preserve lengths, but it preserves ratios of lengths. So now all I need to do is calculate the length of the green part here. Okay? So there is a complication. The complication is that I started from a line emanating from the top of rectangle 0, I end up with a line at some other rectangle. We'll have to deal with that, and we'll deal with that later. Okay. I'm going to call the coordinate of the rectangle which contains the image rectangle number Zn star. N star is the number of matrices in the product that gives me the contraction. Okay. So now how do I define the green part of this line here? So by definition, this is the part of the line which, when I apply to it the inverse of the symmetry, brings me to rectangle Xi. Okay, because this green part is the image under Psi of this green part. Therefore, the set of points in the green part here is defined by the condition that Psi inverse maps it to rectangle number Xi. Okay? Thus, we have the following formula. The relative size of the green, okay, here, is the relative length of the points at this segment, which Psi inverse maps to rectangle Xi. But this is the measure with respect to the Lebesgue measure, and it's the relative size. So it's like the probability that if I choose a point randomly uniformly on this segment and apply to it Psi inverse, I end up at rectangle Xi. I start at rectangle Zn star, and after I apply Psi inverse, I end up at rectangle Xi. So now you see that I'm moving from geometry to probability. Okay? So now I'm recasting this quantity, the number of times that the error term equals a specific value. I'm translating it into the probability that if I choose Q, a point Q, randomly uniformly on this shortened line, and I apply to this point Psi inverse, I end up at rectangle Xi. Okay? Now, what is Psi inverse? Let me remind you, it's the symmetry which has a derivative given by the product of these matrices. I can write this symmetry as the composition of symmetries, each corresponding to its own matrix. Okay? And now I have the following, here is a cartoon of the situation. I'm choosing a point randomly uniformly on a line segment, strictly inside rectangle Zn star. Okay? And I want to know what's the probability that after I apply psi inverse, I end up at rectangle Xc? But I can think about what happens when I do it step by step. When I do it step by step, I'm starting to perform a random walk on the staircase, okay? Each component in the product moves me at some step. So the first one moves me from here to some other rectangle. The second one moves me to some other rectangle and so on. And the question is, what's the probability that when I complete this walk, I end up exactly at rectangle C? So this is similar to a random walk, okay? I'm doing a random walk. I'm starting at rectangle Z and star. This is the one here. I want to know what's the probability that I end up at rectangle C, okay? Starting here. So I want to move from this height to this height using steps driven by these symmetries psi I, by these matrices. So this is like calculating the probability that a random walk starts at a certain height and ends at a certain height. This is exactly what the local limit theorem is about. It's about the probability that a random walk after n steps makes a definite step. Okay, in this case, the step which takes me from height Z and star to height Xc. Okay, so I can now write the quantity which interests me as the probability that the sum of the steps due to each symmetry exactly equals to Xc minus Z and star, exactly equals to the step which leads me from rectangle at height Z and star to rectangle at height Xc. Okay, so this delta Zk, these are the steps performed, which I performed due to the corresponding symmetry, the corresponding matrix. Okay? Okay. Any question about this heuristic? Okay, so now I don't have much time, so I will just tell you that this random walk can be very well approximated by a random walk performed by an inhomogeneous Markov chain. The Markov chain is inhomogeneous. The transition probabilities change from in time because you are applying different symmetries at each time. You are applying different psi's at each time. Each psi corresponds to one of those upper triangular or lower triangular matrices which appears in the product. This is why the transition probabilities change in time. This is why you get a random walk driven by an inhomogeneous Markov chain. However, when you analyze this Markov chain, you see that it's a very nice Markov chain in the sense that it satisfies a technical condition called Devlin's condition, which implies that it's uniformly exponentially mixing. And it has some other nice properties, which I don't have time to explain. And what is crucial is that under these technical properties, we can prove something called a local limit theorem. The local limit theorem is exactly is the statement which exactly tells you what is the asymptotic behavior of the probabilities that the random walk performs a given step at time n. And that exactly gives us the asymptotic information we need. Of course, you need to apply this local limit theorem for an inhomogeneous Markov chain, and this was the main technical point, and this is why it took us 10 years, because it took us time to develop these local limit theorems in the inhomogeneous case. But anyway, now this is done, so it's written. And here is the local limit theorem. It's a bit complicated. Basically, what it says is that you have an asymptotic formula for the probabilities that the random walk is equal to a specific value. It behaves like 1 over times 2 pi variance, the variance at time n, times the density. Density is evaluated at some function. Looks very complicated, but it turns out that there are uniformities. So the quantity here is approximately 1/2 the square, and this quantity is approximately 1. So you can you have control of the right-hand side in this asymptotic relation. And when you apply these controls and you take the ratio of the probabilities, you see that things cancel out and you get 1. When? If the target, the z and k that appears here divided by the variance, tends to 0. Under this assumption, it's an assumption on z and k, the height of the rectangle you map to. Under this assumption, you can deduce from the local limit theorem that the ratio converges to 1. Okay, so now let's move back to the original problem. Basically, what we got, we started from the error at Weyl's theorem. We want to know when do different values are equally frequent. We used a sequence of reductions which transforms this ratio to the ratio of probabilities, local limit theorem probabilities for a certain random walk driven by an inhomogeneous Markov chain. And we saw, due to the local limit theorem, that if Zn star, the coordinate of the rectangle you end up with after applying the shortening symmetry, if this quantity has the property that Zn divided by Vn tends to 0, Vn is the variance, then the local limit theorem applies and you get that the limit is 1. It turns out that the Vn always, the variances are basically linear, so all this works subject to the assumption that Zn star divided by n star tends to 0. Okay? You can ask what happens if this is not the case. Well, you can prove that if this is not the case, then there is no equidistribution. So after all this work is done, okay, I'm going to skip the reasoning. Why? After all this is done, you get the following consequence. You have equidistribution if and only if Zn star divided by n star tends to 0. If Zn star divided by n star equals to converges to 0, you can apply the local limit theorem and get that the limit is equal to 1. If it's not doesn't converge to 0, you can use something called the local limit theorem for large deviations to see that the limit is not always 0, not always 1. So you get this equivalence. Now it remains to decide when is it the case that this condition holds. When is it the case that Zn star divided by n star converges to 0? Specifically, for which alphas is it the case that the sequence of symmetries that you obtain give you this condition? Okay, so let me remind you what was Zn star. Zn star is by definition the height of the rectangle which contains the beginning of the line after you apply the symmetry. Okay? That's the definition. And what was Mn star? What was the symmetry? It was the symmetry that you build from the product of these matrices. So everything is concrete and everything can be calculated. So we calculated what was Zn star. And guess what? We got that Zn star is given by this formula. If the even continued fraction expansion of beta is given by this sequence, then we know the matrices and we can calculate by hand what happens to the line when you apply to it the symmetry is associated to this matrix followed by this matrix and so on. And we calculated and saw that the height of the rectangle which contains the beginning is given by this sum. So this gives the proof. Equidistribution happens if and only if this limit is 0. That's because of the local limit theorem. And a calculation shows that Zn star is proportional to this sum. So you get that you have equidistribution if and only if the limit of this averages is 0. And that's the way that the proof goes. And that's the end. So thank you very much for your attention.
Thanks a lot for this wonderful talk. Let's collectively thank Omri for this wonderful talk. How does one clap? Okay, I don't remember how this works. So questions.
I can't read comments on
Sure.
the chat because I'm sharing my screen, but
I will read them out for you, or I'll ask
Okay.
a person to read it out for you.
okay.
So I have one question. In the case when it does not equidistribute, do you are these points generic for some measure? Is this
Okay, so generic in the sense of dense G delta?
no? So you're starting at you're looking at the ergodic sums starting at 0. So not in the sense of G delta. I meant to say, is there some okay? So it's not uniform in the integers in some sense. Is there some other distribution that it is following?
Okay, that's a very good question. We have a characterization of the situation when we have a characterization of the situation when it's generic for one of the other measures discovered by Nakada.
I see.
But what is much more common is for it not to be generic for any of those measures.
Oh, so
the reason is the following. Basically, if the drift is 0, then you are generic for Lebesgue measure. If the drift is non-zero and is not too big, then it's generic for one of the other measures. But what is much more common is that there is no drift. So when you look at the sequence Zn, you can concatenate, you have the freedom of concatenating different segments in the even continued fraction expansion. So you can have the alpha to behave at the beginning like one measure, and then behave like another measure, and then behave and fluctuate in this way. So I would say that this is the most common scenario. When it's really not, when it's really wild.
Right, but I guess one could. Okay, now I guess this question is becoming more and more contrived as I go about it. If you looked at it subsequently, then perhaps is there an identification of what limit points you would get for the? But then what would that even mean? Yeah, okay.
No, that's a good question. That's a good question, and the answer is no. No, it's an open problem. For the whole cycle flow on Z covers, we do have a characterization. But for this, we do not. We know that if you go beyond bounded type, and you look at typical numbers alpha, then usually you will have subsequences along which, instead of the Gaussian limit theorem, in Beck's theorem, you have uniform distribution.
Right.
But we don't know what are all the limit points. It's a difficult question.
Other questions?
I have a question. Hope it makes sense. If I try to do another skew product, say the rectangles, I cut them, paste them to give the plane with some obstacles. I mean, you get some joint distribution of two rotations or something of that sort.
That's a very, very interesting question. What you're describing is called the wind-free model. It's very, very interesting to understand what happens there. It's much, much, much more difficult. It's an order of magnitude more difficult than what I was discussing. But it's a very interesting model. It has been studied by Krzysztof Franczek and Corina Ulczykaj. You can also do other types of periodic translation surfaces. In principle, in general, I don't know of any other case where people were able to determine the generic points for straight line flows. In some sense, this was one of the motivations for this work. You understand what I mean?
Yeah, definitely. I also work on it. I know the Z cover case are much more understood. When you go to other dimensions, we don't know nothing about genericity.
Yeah.
So I hope maybe something would come out of it. We'll see.
Yeah. So the question of ergodicity was studied, if I'm not mistaken, by Ulczykaj and Franczek.
But wait, higher dimensions, do you mean in, say, three-dimensional?
When the symmetry is not Z, when it's not a Z symmetry, but
sure,
it's
sure.
Z to the power Z,
okay.
Even Z to the power. For example, it's very interesting to look at the Z2 array of rectangular obstacles and study the billiard flow there.
Of course.
or take a Z2 array of slits and study with some identification rules and study the straight line flow.
There's a question by Carlos. You can unmute yourself and ask your question. Otherwise, I can, if you have a problem with your speaker, I can do it for you.
Oh no, I can talk.
Please go ahead,
So my
Carlos.
question is, my question was about the drift case. You mentioned some measures, sorry, some distributions for the Nakamura results, but are all these drift cases completely classified, or there is no way to classify the distributions?
Okay, so what has been classified is the collection of ergodic invariant locally finite measures. Okay, so we know what all the ergodic locally finite measures are for the linear flow or for the cylinder map. This was done in this paper by Aronson, Nakada, Rita Solomiak, and me, and by Huber and Weiss for the flow. The work that I was talking about today is closely related to a problem which is solved on classifying the generic points for these measures. There is another question, which is if you look at Beck's theorem, maybe I will go to this slide. What do you see now on the screen, by the way? I still share the screen, right?
You're still sharing the screen. I see summary DN alpha. Okay, now I see irregularities. So I think it's your first slide or something.
Okay, so let me go here. Okay, so you can ask, suppose you take alpha and you look at the histogram of the errors, and Beck's theorem tells you that if alpha is quadratic irrational, then the histogram has a scaling limit which is Gaussian. And this is also true for alphas of bounded type. It's a theorem of Bromberg and Ulchigrai and Dolgopyat and me, depending on what you assume on the interval. And you can ask what happens for other alphas, for alphas which are not of bounded type. And there, very often you do not have scaling limits, which means that along different subsequences, you see different shapes. And Nishant asked the question, what are the possible shapes that you see? So this question is very interesting because there is another scenario, a scenario of Horo cycle flows on ZD covers of hyperbolic surfaces which are non-compact but of finite area. In that case, there is an answer to that question. You know what are all the limit points. But for the question arising from N alpha mod 1, this question is open, still open. Is this what you meant?
I think so. It sounds like you cannot sometimes, like what I understand from what you're saying is like at some point you don't see shapes, right? Regular shapes on this curve, in the histogram.
You see different things along. You see different things along different subsequences.
Right.
Dima and I show that for almost every alpha, there is a subsequence where you see the uniform distribution, for example. And there is another subsequence where you see, now I could be wrong, I don't remember it precisely, but I think it's the convolution of the uniform distribution itself. So these are two different distributions. We don't know what are all the possible things that you see. By the way, if you play this game for a highly chaotic dynamical system like an Anosov diffeomorphism, then it's a theorem that you see all possible distributions in the world for almost every initial condition. For almost every initial condition, for any possible distribution in the world, there will be a subsequence where that's what you're going to see. So it's very, very wide. But in these zero entropy rigid scenarios, maybe there are some constraints. It's open.
Are there more questions? Okay, let's thank Omri for this wonderful
Thank you
talk.
for your attention. Thank you.
Stop recording.